right, so here we have a pendulum that's 3 kilograms. It is attached to a small metal ball to one end of a string that is 1.6 meters long. And it says the ball is released when it is raised high enough for the string to make an angle of 50 degrees with the vertical. All right, and it says here assume no energy is lost. So this is a conservative system. So in the diagram, you have a mass here that's raised, like I said, it's 50 degrees measured from the vertical axis here. All right, the length of the string here is labeled L. Keep in mind that it's given to us as 1.6 meters. So let's go and crack this out. A, B, C, D, and E. Pause the video if you need to. All right, in order to do part A, it says calculate the initial gravitational potential energy of the ball at point A, which is here. The ball is raised 50 degrees towards the left there, and then it's going to be released from point A. So in order to find PE, you need to find H, okay? Because PE due to gravity is H dependent. Here H is measured from ground up, so the function for it is mgh. Well, all you have to do is find H. You're given M is 3 kilograms. You're given G is 9.8, right? All we have to do is find HI, or the initial H. How high is it above the ground at point A? So to do so, I'm just going to show you how to do a little quick geometry here. This is the most important skill for these types of problems, so hopefully keep up with this particular part. And if you need to, like, watch it again. It has to make sense, otherwise you're going to make a super doable problem into a really confusing problem, okay? So here, I'm just going to segment from the location A to B. B being the lowest, A is where the object is raised initially to a height of whatever this H is. So I'm just going to call this H, okay? So here's H. I need to figure what that H is, right? So here's how you do this stuff, okay? Well, I know the length of the string is labeled as L, which is 1.6 meters. Once again, it's given. Well, as the pendulum swings up and down, or back and forth, or I'll say if you want to say that, the length of the string cannot change, right? It's like a swing on a playground. The length of the chain cannot change. So here's that same concept. So whatever L is, L has to stay constant throughout the whole entire motion, okay? Well, if that's the case, if this is L, I can break L into a right triangle. Watch my cursor. This is my hypotenuse. I can make it into a right triangle, okay? Now, I'm only concerning with this particular leg that came up here in the right, okay? So this arrow here. I don't really care about this length. Why? Because I'm trying to find H. So I need to focus my attention up and down. Well, if you look at this right triangle, this is your adjacent leg. Now, L being your hypotenuse, here's your angle, and your angle, excuse me, your angle touches this leg that I just drew up in the orange arrow. And from this perspective of 50 degrees, this is your adjacent. So this right here is L cosine of 50. It's cosine because it is the adjacent leg. So we take, to find the adjacent leg, we just take the hypotenuse, which is L, and we times it by the cosine of 50, okay? Once again, it's cosine because it's adjacent. Well, but I'm not done yet, right? That just tells me that segment there. Well, I know the length of the string is L. So the second arrow in channel that just came up here, that's pretty close to it. Once again, the string cannot change throughout the whole entire flight. So that's L. Well, I don't need L, and I don't need L cosine 50. What I do need is this H in blue, okay? So you can just do a little math. From top all the way to bottom is L. From top to where this dashed line is L cosine theta. So H would just be the total length minus the upper length. You minus because that's, well, in order to find L, you have to add L cosine 50 plus H. So to find H, you just subtract, okay? I'd like to say common sense here, but just in case your math is not solid. All right, therefore, to find this missing H here, L minus L cosine of 50 degrees, and that is your H. Well, now we can find H super fast, right? So therefore, I carry my work over here. H is equal to L minus L cosine of 50, L being 1.6. And then that's it. So here, if you like to, you can leave it as L, which is 1.6 minus 1.6 times cosine 50. But what I like to factor out is I like to factor out the L because L is in the first term, L is also in the second term. But when you do your work, you decide if you need to if you want to factor out or not. I just like to factor things out. All right. Other than that, here's L being 1.6. In the parentheses is 1 because when you factor L out, it's just 1. And then when you factor L from L cosine of 50, it's just cosine of 50. So all you have to do is punch it in your calculator. So 1 minus cosine of 50 do that first and then times it by 1.6, and you should get a height of 0.57 meters. So that's our answer for part, excuse me, that's going to help us find the answer for part A, okay? Because now that we have HI, we can just plug it back into PE. So PE once again being 3, 9.8 times HI here being 0.57, and if you punch in your calculator, your potential energy initially is 16.76 joules. All right, that's that. Let's do part B. Part B wants us to find the speed of the ball at the lowest point of the swing. So here, I'm just going to use conservation mechanical energy because it's conserved. It says assume no energy loss. I know the initial energy must equal to the final energy. Here, I'm just going to expand MEI and MEF into their components. PEI plus KEI equals PF plus KF. I'm going to cancel KEI out because it starts at rest. Okay, it says it's raised and then release. So therefore, I'm just going to also cancel out PEF in this particular part because it says the lowest point being B, and B having no height. So it reduces down to pretty simple function. PEI is just MTHI, KEF is just 1/2 MVF squared. And then here, the mass cancels out. And then to solve for VF, because that's what it wants the speed at the lowest point. All we have to do is multiply both sides by 2 to get rid of this denominator in the right side here. Or I just like to move it up to the left. That would be the same as multiplying. And then here we have VF squared. So we know HI already, so we just plug and chug it. Okay, 2 got carried down. 9.8 is in the parentheses, HI being 0.57. And here to get VF by itself, you would have to square root. Okay, so I just have here the final speed at point B being about 3.34 meters per second. And it says speed, so I don't need to provide a direction. But at the lowest point in this diagram, if it asks for velocity, instantaneous velocity, you would just say 3.34 meters per second pointing rightward. At that point, the arrow is pointing rightward. Okay. All right. And that is the answer to part B. That's the speed. Let's do part C. All right. Part C asks you to find the magnitude of the tension at the lowest point. So this is a centripetal force component. So I'm just going to clean up my diagram a little bit here. Okay. Well, in order to find the tension in the string at the lowest point, I'm just going to draw out my free body diagram. Here is F of G acting on the pendulum or the steel ball that's pointing down the page. Well, as it swings, there's a tension in the string. And the tension in the string at this particular location, at point B here, at the lowest point, will always be greater than F of G because it's constantly moving. Okay, so there's a force that's causing this bob to continuously rise over here. Therefore, I'm going to go ahead and set up a centripetal force. Centripetal force is just going to be T minus F of G, T being greater and pointing up here, subtracted from F of G, which is acting against it. And then from there, to solve for T, I'm just going to expand F of C into mv squared over r. I know what m is, which is 3. I just found v in part B, which is 3.34. I know what my r is. R here being just the length of the string. Okay, so don't overcomplicate this r. For this type of problem, r is the length of the string because it traces out a circle. So you pivot would be where the ceiling is, and then all the way to the bottom, that's your radius of the circle, and that would be the length of L. And then mg F of G is broken into mg. All right, other than that, to solve for T, move this negative F of G to the left side. So T is going to equal to mv squared over r plus mg. Okay, keep in mind the negative sign's already taken care of for you here in G. So make sure you plug in a positive 9.8 when you get to this step. All right, other than that, I see an M there. I see an M there at this point. You decide if you want to factor out the M's or not. I'm going to go ahead and factor out just for fun. All right, here. So this term has an M, that term has an M. I'm going to factor it out. And then here, you just plug and chug, okay? M being 3 kilograms, and then V squared. So if you take 3.34 square that, you'll get about 11.16. And then the length of the string, which is R, is 1.6. And then here, G, once again, is positive 9.8. And all that on your calculator will give you a magnitude of about 50.34 newtons. There is a bit of rounding involved here because there's decimal involved. All right, so that takes care of A, B, and C. Let's go D and E. Part D asks you to find the height at point C. Okay, so I'm going to do this one more time. Okay. In order to find the height here in the diagram, once again, just follow what I did in part A. If you didn't, go watch it again. I'm just going to segment this part because that's what H is in this diagram for this particular segment. Okay, so now it's on its way up, right? Therefore, this length here that just came up, that's the length of the string, which cannot change throughout the whole entire problem. Here, that is your cosine, because the L here is your hypotenuse. 14 degrees is given touching this particular angle. It touches the y-axis and your L here. But here, this arrow that just came up, that is your adjacent, because it touches between this angle. Okay, it's adjacent for this angle. And then, so we would apply the same stuff. It would be L cosine, because it's the adjacent leg. Well, the degree here would just be 14 instead of 50 as in part A, because this is now 14 degrees on this way up. Well, we know what L is, and we can just find that length really fast if you wanted to punch in your calculator. All right, but more importantly, on the bottom here, this red arrow is what you're trying to find. Okay, so to find this H, all you have to do is take the length of the string, which is top, all the way to B. That's L. But from here to here is L cosine of 14. So to find the remaining length, you would just take the whole length, which is L, subtract it from what has already been used, which is L cosine of 14. So the height here is L minus L cosine of 14. Same strategy that I did in part A. So if you need to, go back and watch part A again, okay? Other than that, to find H, super light work here. H is equal to L minus L cosine of 14 degrees. I'm going to factor out L, and then I'm just going to plug in chug. L being 1.6, there's 1 in parentheses. Cosine of 14 is just some number. And if you simplify all this on your calculator, you should get a height of about 0.048 meters. Okay, so that's the answer for part D. All right, let's go E. E asks you to find the linear speed, okay, at point C. So as you can see here, I have an arrow that's pointing tangentially to the circular path. All right, so there's V. Okay, and that V I drew just a little shorter than this V in the bottom, only because as the steel ball rises, it slows down, and that's just a common sense thing. Okay, there's a FGX or an F of G component that acts against it, causing it to slow down. But I won't address it in this one. Here, I'm just going to set up conservation mechanical energy again. Okay, the only thing I have to caution you is that don't make false assumption here. At this point C, the steel ball is moving because it asks for V, but it's also at some height above the ground. Okay, so it has a KE and a PE. All right, so I'm just going to go from point A to C. If I start at point A, I can cancel out KEI being 0, and then I can just expand everything else. All right, PEI, once again, is MTHI. PEF here exists because it is above the ground, or above the lowest point being point B, and point C, using common sense, is higher than point B, which imply that there isn't a PE due to gravity. All right, so you break all this stuff up, and as you can see, mass cancels out. Okay, here, I'm just going to move GHF to the left side, which makes it negative. And then here, I'm just going to multiply everything by 2. Okay. Once again, if you notice, I factor out the G there, and I'm just going to multiply everything by 2. And then this is VF squared, so I want to plug and chug. 2, G is 9.8, not negative 9.8, right? This is positive 9.8. HI being 0.57, which I found in part A. HF being 0.048, which I just found in part D, right here, right? And this is VF squared. And if you plug all this in your calculator properly, you should get about 10.23. And then to find VF, you would just take the square root to get rid of the exponent 2 here. So therefore, VF, which is equal to the square root of 10.23, which will give you about 3.2. Which makes sense, because the speed at the bottom is, I think I calculated was about 3.34. So as it rises, it has to slow down. So 3.2 is reasonable. I just know that it has to be smaller than 3.34. Okay, and here the angle is small, so this seems pretty reasonable. All right, hopefully my calculator works out here. Other than that, there is another way to do it. Okay, if you wanted to, right, for part E, once you get to this point here, I want to point out, once you get to this point, right, it's entirely up to you how you want to tackle these types of problem. Here, you know what mass is, which is 3. It's given in the problem. You know G is 9.8. You know HI is 0.57. So you can just plug and chug. Okay, so what I want to do is I'm just going to plug and chug here if you wanted to. It's just more calculator work. Here, you plug in 3, G is 9.8, HI is 0.57 because that's what we found in part A. And then here, M is 3, G is 9.8, HF we just found is 0.048. And then the 1/2 stays, and then M here is 3. And then here's VF. And if you wanted to, you can just do it this way and just calculator work and then just find VF and it will give you the same answer. So it's entirely up to you. I like to work my stuff out in variable first before I plug and chug. All right, other than that, stay nerdy, don't be wired.